Well, hello everyone, and welcome back to Epidemiology. I'm in my office today, and you can look out the window and see behind me, we're on the campus of the glorious University of Ottawa. So this is the second of the lecture videos I promised I would upload because I cannot make in person the October 13th, the Friday the 13th class, which is tomorrow. And the topic for today is one of my least favorite topics. It is the Kaplan-Meier survival curves. And for some reason, I have this intellectual wall that prevents me from approaching this topic with any sense of decorum or calmness. And I tell every year, I've been teaching this class, 7, 8, 9 years? I have no idea. But every year I tell the students how much this topic freaks me out. And I think the reason is that when I learned it as a student, I didn't fully understand it at first. But every year that I tell students this, they turn around and tell me, this was one of the easiest things you've ever presented. Why are you so freaked out by it? I don't know. That's the nature of psychology. So let's not dilly-dally too much longer. We're going now to look at survival analysis and the Kaplan-Meier method of constructing these survival curves. Why is my face all dark? Why is that? It's because the lighting is so poor. Can I fix this? Does it matter? Doesn't matter. You don't need to see me. Fantastic. I did record a version of this same lecture back in 2014 that wasn't as slick as this one. It didn't involve any screen captures. It was just a camera on my face in class. So if you want to see a different version of this lecture, you can look at it at that link. It's whatever. It's there for you. Okay, remember this? We talked about survival very briefly in an earlier lecture. And we looked at these 6 people who were being observed over a period of 5 years, and we said that 2 of them, C and F, died while we're looking at them. 2 of them, A and D, did not die. They were alive at the end of the 5-year period. But 2 of them, B and E, we don't know what happened to them. They were lost to follow-up. They disappeared. Maybe they moved out. Maybe they changed their phone numbers. Maybe we lost their phone numbers. But we don't know what happened, so we say they are censored. Censored means we don't know what happened to them. All we know is we are no longer tracking them in the study. So because they didn't die, we can't say that they did. And this confounds and really complicates our survival analysis. If we were to assume that they died, then really out of the 6, only 2 people survived, A and D. If that's the case, our survival rate is 33%. Very, very poor. If we assume that they lived, then 1, 2, 3 people survived, or 4 people survived rather, and that's 67%. That's a huge difference. So how we deal with these censored individuals, these people whose status remains unknown to us, is critical in how we understand survival. That's why we have this method called the Kaplan-Meier method, which we hope, accounts for this uncertainty in censoring. That's why we do it. So, because of the loss to follow-up problem, we have this thing called survival analysis to account for the uncertainty of what happens when these individuals are censored. And there are lots of different kinds of survival analysis. We're going to learn one today that uses a thing called life tables. And life tables are an actuarial process of keeping track of individuals or populations at various moments in time. And the method we use is the Kaplan-Meier method. Let me cast your minds back several centuries, though, to the origins of modern statistics. And I'll suggest to you that much of what we think we know about statistics actually comes from astronomy and astrophysics, space sciences. Christian Huygens was a famous, I believe he was Dutch astronomer / mathematician back in the 17th century. And you may recognize his name, or not. It's attached to the Huygens space probe. So Christian Huygens created one of the earliest known survival graphs, and here it is. This is from 1669 that showed how many out of 100 people survive up to 86 years. Let me see if I can make this a little larger. That's better. So here we started with 100 people, and as time goes by, there are fewer and fewer and fewer people. So if we ask ourselves, what's the probability of living to 20 years, or 36 years, or 76 years? Okay? We can figure that out based on this graph. So at 20 years, there are about, what, 32 people remaining? At 36 years, there are about 16 people remaining. At 76 years, there's one person remaining. So we know the probability of living past 76 is 1%. Of living past 36, 16%. Living past 20, about 32%, etc., etc., etc. So this is a very basic way of looking at survival analysis. Now, back in the 2000 BMJ, here's an example. This is a cohort study looking at survival after a heart attack, a myocardial infarction. Let me expand my screen here for a second. Let me see if that's... okay. I didn't make my screen the right size. So here you see one way of looking at survival analysis is comparing curves. So in this particular cadre of individuals, if you took the aspirin alone, your population fell off like this. So we see you have a lesser chance of being alive after 350 days if you took aspirin alone versus if you took aspirin and ibuprofen. And the advantages accumulate the more time goes by. That is an effective, realistic way of using survival analysis. It allows us to compare different therapies in terms of their ability to prolong survival. When using the life table method that I will show you today, there are some assumptions we have to make. The first is that there is no change in the effectiveness of the treatment or the diagnosis over time. Now, diagnosis is not an issue if the outcome we're looking at is survival, because we can tell pretty well if you're alive or dead. But sometimes the outcome is not survival. Sometimes it's pregnancy. Sometimes it's remission, presence of a disease, right? In that case, the ability to diagnose that disease must remain constant throughout a study period. Otherwise, that changes the nature of the data. The same with the effectiveness of the treatment. If the longer you live, the more likely it is to be effective, then that biases the evolution of the curve. The second thing, and the most important thing, is the survival experience of the people lost to follow-up has to be assumed to be the same as those who were followed. What does that mean? It means if you're in a study and we're watching to see how many people in the study survive a certain length of time, and we lose track of 5 people, if those 5 people left for a reason that's relevant to the study, like maybe they were so critically ill they're about to die anyway, and so they went off to die on their own, well, we need to know that because they were a particularly vulnerable and likely to die population that would have reduced our survival rate. So in absence of knowing that, we have to assume that they have the same chance of dying as everybody else. So it's important that when we do survival analysis, we do so on a topic for a therapy or an intervention that does not confer any particular advantage or disadvantage depending upon if you are lost to follow-up or not. Now, it's important to know as well that life table analysis, even though we talk about them as survival curves, survival of course means living or dead, it's useful for anything for which there is a dichotomous outcome. I'm going to show you later on an example using pregnancy as an outcome. Either you're pregnant or you're not. That's dichotomous, right? So it doesn't have to be about dead or alive. It can be about anything for which we can determine yes or no as an outcome. So life table analysis in general is a technique used to describe mortality and survival in a population. And I mentioned that a lot of this comes from space science and astronomy, so you may not be surprised to see this name. First used, life table analysis was first used in the 17th century by Edmund Halley. Do you recognize that name? From Halley's Comet? So Edmund Halley was the first astronomer to predict that comets were in fact recurring, and he predicted the return of Halley's Comet. And in 1815, the first accurate life tables were published in the UK, and today we rely upon them heavily. The science of actuary is based entirely on life tables, and if you're looking for a career to build that is lucrative, mathematical, and a little boring between you and me, actuarial sciences is one you might want to consider. There are, in general, 2 kinds of life tables, the current and the cohort. So the current life table is the one that's used most commonly by insurance companies and governments and actuaries. And it's talking about the mortality rates of a large population. Usually the data refers to what's happening at the middle of a time interval, like midday, midweek, mid-month, mid-year, whatever it might be, for a large bunch of people, like all men or all people of a certain ethnicity, etc. The cohort life table, on the other hand, is talking about the specific experiences of a group of people. Not their average, but them in and of themselves. And this is rarer because most commonly we don't have access to data for the same people over a period of time. However, for the Kaplan-Meier method that I'm going to show you today, that is an example of the cohort life table method because it is applied to a small clinical group of people that we can observe over time. So the cohort life table method is really useful for clinical studies, as we will see today. This is an example of the life tables for Canadians computed in 2004. It's just an example of what things look like. So here we see the portions of people still alive in certain age groups. And unsurprisingly, most people are still alive in their extreme youth, and fewer people are still alive after 95 to 100. By the way, it may amuse you to know that the fastest growing age group in North America is in fact centenarians, people over 100. It doesn't mean there are a lot of them, it just means that as an age group, they're actually growing the fastest. So, let us look at some of the terminology before we actually do an analysis. First is the time to event. This is the time from which you enter the study to something happening to you. What's going to happen to you? Well, either you have the outcome we're looking for, which is probably death. It doesn't have to be death, but it's whatever we define as being the outcome we're looking for, usually is death. Or it's when we lose you to follow-up, or you're censored. Okay? So the time it takes from the entry to when something happens, time to event. Next is this word censoring. I mentioned it a few times. I want you to get used to it. Censoring is what happens when you leave the study for reasons other than the outcome being achieved. So you didn't die, you didn't get pregnant, you didn't get the thing we are looking for, but you still leave the study. Censoring is the reason we're doing this, because we don't know what's happened to you. We count you as alive, still in the study, up until you are censored. Then after that, we don't know what to do with you. Right. Survival time that's what we're measuring. It's the time from the beginning of your participation in the study. Not from the beginning of the study, but the beginning of the individual's participation in the study. Now, for a lot of people, survival time is not complete. For what people? The people who were censored, because we don't know what happened to them after they were censored. Did they survive or did they not? Censored data is a problem because, as I showed you in the very first couple of slides, depending on how we look at the censored data, if we assume that they died, we get one answer. If we assume they're alive, we get a different answer. So it's important that we know, to the best of our abilities, what happens to those people, but often we do not. Right censoring is a very important thing that we do. It is when we pretend that everybody in the study started at the same time. This almost never happens. So think about this. Think about if we're enrolling people in some study about their survival after taking a drug after getting a heart attack. Ideally, we start our study in January and we continue it until December, 1 year's worth. In January, how many people have heart attacks in the clinic that we're working in? I don't know. Probably not the couple of hundred that we need for a study. So we have to wait several months and enroll people as they have heart attacks and agree to be in our study and agree to take the drug that we're testing. But because everyone starts at different times, I can't then say for my 1 year, I'm going to look at 1 year's worth of data, because some people have 6 months worth of data, some people 3 months worth of data. Instead, what I do is I do this. So here we have 1, 2, 3, 4 people who are being monitored in a study. So this person here, subject number 2, started in October of '89. This person, subject number 4, started in January of '91, and they died in April of '91, and so forth, right? They're starting and ending at different times. What I do is I right censor, meaning I move everybody to the left. I pretend that they all started at the same time. The duration of their stay, i.e. their survival time, does not change, but I pull the lines over so that the left side of my graph all lines up. It's unfortunate that we use the word right censoring, because I've already told you that censoring is a bad thing. It means that they've left the study for no reason. This is different. So censoring is different from right censoring. A censored individual has left the study. We don't know where they are. A right censored individual, we've just moved them to the left so that their start time lines up with everybody else. Okay, here's an example of how to look at survival data in a quick way and garner some insight and wisdom. This is all-cause mortality for Western nations. Look at this. So, in Western nations, pretty much everyone's alive up until 30s and 40s. Hit their 50s, a few start dying. In the 60s, they start dying a bit more, but majority is still alive. It's not until you get to like the 70s and 80s that the majority of people are dead. Right? So mortality starts increasing dramatically in the 70s. But you can expect most people to live up until 70 or so. Fine. Then we look at so-called third world countries, which, by the way, we don't use anymore. We say low-income countries, but okay, fine. Third world countries. Same data approach, but look at this. Instead of having that curve, we have this curve. Right? So the majority are dead by the time they're 10 years old. What this tells us right away from comparing those two curves is that the main demographic difference between wealthy countries and poor countries is survival in extreme youth. Right? So these countries, the Western countries, really benefit from having really good prenatal care, child care, basic healthcare systems so that their youth don't die. A quick insight gleaned from looking at those two curves quickly. Right. We're going to talk about the Kaplan-Meier curve now, the heft of this lecture. This, by the way, is Gabe Kaplan, an actor from the 70s that none of you recognize because you're all so young. Damn you kids. Kids. I'm going to show you two ways of doing this. The hard way and the easy way. The hard way isn't that hard. But as I told you, I've got this mental block regarding the Kaplan-Meier method. So I'm going to struggle through the hard way, and you're going to struggle with me. Then I'll show you the easy way, and you'll say, why didn't you just show me the easy way, Ray? And I'll say, well, because there's two ways, right? So, and they both tell the same story. And the math is really quite simple. It's just getting your mind around what you're dividing. Because, like everything else in epidemiology, this is really about dividing two numbers. And the problem is figuring out which two numbers to divide. So the Kaplan-Meier curve is actually relatively new. It was invented in the late 50s by two guys named Kaplan and Meier. Didn't see that coming, did you? So this is Meier in 2006. I don't have a picture of Kaplan, but I'm sure he's a handsome man. And the Kaplan-Meier method is used to measure the fraction of people living after a certain amount of time. Okay? So usually in a clinical environment, so treatment or intervention with a drug usually. In economics, we use it to measure the length of time people remain employed. Right? For example, after a factory shuts down. We can use it in engineering to measure the time until parts can fail. We can use it in ecology to estimate how long certain plant parts remain on the vegetative body over time. It's a really useful statistical tool that has really spread across many disciplines over time. So maybe you can use this in whatever you end up doing with your careers. It is a non-parametric test. If you remember your statistics, you know that parametric tests involve some global distribution that we're trying to access. There's none of that going on here. It's simply a fraction of people alive after a certain amount of time. And we usually use it to describe, the proportion of people who are alive in a study, but it doesn't have to be. We can use it for any particular outcome, not just death. And usually we use it to compare two outcomes, like a drug versus a placebo. And it gives us a very easy graph to look at very quickly and understand what's going on. If you want to see how it manifests in real time, you can go to this link and there'll be a Java simulation, and you'll see that as our sample size increases, the Kaplan-Meier curve starts looking like one of those Gompertz curves, or the very first Christian Huygens curve I showed you from 1669. But the Kaplan-Meier curve is going to look jagged, and you'll know why when we do it. But the more sample size we have, the less jagged it becomes. This is the jaggedness I was talking about. So this is a real analysis. We have two drugs in a population. Let's say we've got I don't know, 20 patients enrolled. We've got half of them are taking the drug and half of them are taking a placebo, right? The red is placebo, the green is the drug. And we see after 1 year, a few more of the placebo are dead than are the treatment. By get to 3 years, a large proportion of the treatment ones are still alive versus a smaller proportion of the control ones. So using this technique, we can see that, yes, after 3 years, most of my population is still dead. However, they are less likely to be dead if they're on my new drug. Right. So the Kaplan-Meier curve represents the proportion of the people that we started with who are still alive at different points in time. Now, as time goes on, more people are dead. Okay, that's the nature of a survival population, especially a clinical population, people who've had heart attacks, for example, or extreme cancer. Right. As a result, the left-hand side of our graph, which represents an earlier time, is going to have more sample size than the right-hand side of the graph, because on the right-hand side, more people are dead. The thing about sample size is, the more sample size you have, the more accurate your estimate is. As a result, the early portion of our study is more accurate than the later portion of our study. I'll say it again. The earlier portion of the study is more accurate than the later portion because there are fewer people in the later portion. And that's one of the really problems with survival analysis in general and with Kaplan-Meier in particular. So let's work through some small examples that will freak you out a little bit before we get to a big example that will freak you out more, and then we'll give the easy method. So here we have a study of 5 individuals. And as time goes by in months, various things happen to these 5 individuals. So subject E dies at 4 months. Okay? Everybody else is still alive. So A, B, C, and D, they're all alive. But at 4 months, E dies suddenly. Dun, 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 dun. Not cool, right? So let's say we're graphing that on a survival curve. Here, as time goes on, 100% of people are still alive here. Fantastic. But at 4 months, something horrible happens. At 4 months, this guy dies. So our probability of being alive comes down. The fraction of people alive at this point is 4 out of 5. It was 5 out of 5. Now it's 4 out of 5. Cool. We're still together on this. Fantastic. What happens next? Well, what happens next is subject A drops out after 6 months. He doesn't die. He drops out. He's lost to follow-up. He's censored. Okay? 3 is still alive. And maybe A is still alive. I don't know. But they're not there to figure out what's happening. But at 7 months, subject C dies. So what's happened in 7 months? 7 months now, we have 2 are dead and 1 is lost to follow-up, and 2 are still alive. Okay. How do we deal with this? Here's our graph again. At this point, we have 4/5 of people are still alive. What happens over here? This is where A leaves after 6 months. We don't know what to do with A. We just make a mark there. A's left. But we don't know what happened. We can't really drop down yet because we don't know. But at 7 months, C dies. All right. So how far down do I get to go down? Remember, here we had 4/5 of people alive, so 80%. This guy left. So now there are 3 people left in the study, not 4, but 3, and now this person dies, and there are 2 people left in the study. So, what do I do with that? It's 2/3 people are remaining, not 3/4, but 2/3. I'll say it again. Here, 1 person died, so there's 4 people remaining. 1 person left, now there's 3 people remaining. 1 person died. 2 people remaining. 2 out of how many? 2 out of 3. Okay, we only drop down when someone dies. If they don't die and they leave, we make a mark of it. But how far we come down depends upon the true denominator. The true denominator here was 3 people, not 4, because subject A left. Okay, and these 2 lived a long and storied life. So 2 survived. So what is the final survival? It's going to be the probability of surviving this first drop multiplied by the probability of surviving the second drop. 4/5 times 2/3. That gives me 53%. So the total survival of this population based on the Kaplan-Meier method was 53%. Okay? Now, if we had used the regular survival function, we would have started out with 5 people, and 3 would have survived at the end. So 3 out of 5 would have given me 60%. Fine. Now, if we had assumed that the person who had left had died, then we'd have 2 out of 5 left. Okay? So I'll say that again. I got a little confused there for a second. If I assume the person who dropped out had died, then survival is about 40%. If I assume the person who dropped out had lived, survival is 60%. Instead, we got 53%, so somewhere in between. The Kaplan-Meier method gave us an estimate somewhere in between, assuming that the censored person lived and the censored person died. That's the power of Kaplan-Meier. It allows us to quantify the uncertainty of not knowing what happened to the censored individual. All right, another example. This is actual data of two drug groups being compared, and we see that the control group here is doing better than the treatment group. So clearly, this treatment sucks. This is actual data looking at survival of a clinical group with Thiotepa versus control. Thiotepa is a cancer drug. So here, Thiotepa is doing better than control. So this would encourage us to conclude that this is actually a worthwhile medication. As I mentioned, as time goes on, precision gets worse because there are fewer people in the population. So, survival estimate gets unreliable as more time goes on, especially if our population size is quite small. The problem with Kaplan-Meier, though, it's mostly descriptive. Right? Yes, I do have a number at the end of all this, but I'm really waving my hands and talking about people coming and going. We can't control for covariates. What does that mean? It means that I'm only looking at people surviving or not surviving. I'm not looking at whether or not their gender had a role, or their ethnicity had a role, or their BMI had a role. I can't control for these other factors. In other analyses, we can. We can do multivariable analyses. It requires categorical predictors. What does that mean? It means I can either look at dead or alive, pregnant or not pregnant, on the drug, not on the drug, disease state, not disease state. I can't look at, my outcome can't be CD4 count or viral load or anything involving a continuous variable. I cannot account for time-dependent variables, meaning if some things are changing over time in my population, I can't really model that using this very simple method. So we're going to do an example now using the difficult method. Okay, the hard way, the way that gives me conniptions. So this is an example of pregnancy as the outcome, right? Not death, but pregnancy. So we want the thing that we're looking for isn't who died, but who got pregnant, who conceived. We're following 38 women who are trying to get pregnant, and they're struggling, but they go through a special laparoscopic technique, a surgical technique to improve their potential to get pregnant. And we're going to follow these 38 women for 24 weeks to see who gets pregnant and when. Are you ready? Here we go. So what's the outcome variable? It's pregnancy or conception, not death. Is this going to be right-censored? You better believe it's going to be right-censored. Why? Because it is veritably impossible to get a bunch of women to get pregnant right away. So all at the same time. So we're going to recruit women throughout the year, and they're going to start getting pregnant throughout the year and start trying to get pregnant and all that wonderful stuff. And we're going to move all their data to the left-hand side of the graph to pretend that we started at the same time. So when we're done, this is what our graph is going to look like. Over the course of 24 weeks, the proportion of women failing to get pregnant comes down to about 24% or so. Okay, so again, survival here is failing to get pregnant. Dying is getting pregnant. These are our data. This is a confusing way of looking at data. I understand that. But I want to show you different ways of seeing data so you get used to it. So these are the months at which the women got pregnant. So in the first month, 1, 2, 3, 4, 5, 6 women got pregnant. 1, 2, 3, 4, 5 women got pregnant on the second month. 1, 2, 3 women got pregnant on the third month. 1, 2, 3 got pregnant on the fourth, and so forth, right? Now here on this column, these are the women who left the study. We don't know if they got pregnant after they left. We don't know if they gave up entirely. Maybe they left because they were getting pregnant. We don't know. All we know is that they left. So they were censored. They were lost to follow-up. When were they censored? Well, one was censored at the 2-month period. Another was censored at 3 months. 2 were censored at 7 months, and so on. Right? So that's our data. Let's see what we do with this now. Let's start with our first time to event. The first time something happens is at 1 month. What happens at 1 month? 6 women get pregnant. Right? So an event happens at 1 month. This is how it looks on our graph. Let's come back again. Right? 6 women conceive. So out of those 38, 32 remain in our survival study. 6 got pregnant, 32 remain. Therefore, the fraction surviving is 32 out of 38 after 1 month. Right? We drop down when something happens, when an event happens. And an event is the thing we're looking for, in this case, a pregnancy. So this comes down 32 out of 38, which is like 74%. Where's my mouse? Where's my cursor? Get back here, cursor. It's here somewhere. Oh, it'll come back in a second. Is it back yet? There it is, right? So that should be about 74%. Oh, sorry, 84%. My math is bad. Okay, so 32 out of 38, 80%. Fantastic. All right. So don't be afraid of this terminology. It's just saying the survival function at a certain time is this. So its survival function at the first time of 1 month is 32 out of 38, or 84%. Fantastic. Next time something happens is, and when I say something happening, I mean the event, not the censoring, the event. The next time something happens is at 2 months. 1, 2, 3, 4, 5 people get pregnant at 2 months. But one person left at 2 months. Notice I've changed this from 2 to 2.1. There's no real reason. It's just a way to remind myself that I'm going to deal with this later. There's a note over here that talks about what that means. I've just added a 0.1 just to remind myself I'm going to have to deal with this in the next interval. Okay, but right now, 1, 2, 3, 4, 5 people have now left my study. At 32 remaining, now I've lost 5. How does that look like? Well, out of that 32, 5 are gone. So 27 out of 32 remain. That's an 84% fraction. So I drop down a further 84% from this last point. How do I do that? Well, I take 84% of my previous 84%. That gives me like what? 71%. Fine. So I've got 27 people left now in my study. Or do I? Remember that 2.1 person? They left. So now I don't have 27 people left. I've got 26 people left. Let's see how that manifests. The next event is at 3 months. So 3 people leave, but that person left before, right? So my risk set is actually 26, not 27. So 3 of those got pregnant, so I've got 23 out of 26, or 88.5%. Drop down. I multiply that by my previous percentages, and now my running survival function is now 62.8%. Fantastic, right? I've got 23 people left now. Next time something happens is 4 months. At 4 months, 3 more get pregnant. But we lost somebody last month. Someone dropped out. So now, instead of having 23 people left, I've actually got 22. Right? So out of those 22, I just lost 3. So it's 86.4. I multiply that out, and my running total gives me 54% survival. Right? So 19 people are left in my study. Next segment, 2 people leave at 6 months, but 1 person left at 4 months. So of my 19, 1 has walked away, and I just lost 2 of those 19 to pregnancy. So 1 person walked away from my 19, so my base is now 18. 2 got pregnant. 16 out of 18 is 88.8%. Multiply it out. My running total is now 42.9%. Okay. 16 people are left. right? And we keep on going blah, 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 down. Right? I won't bore you with all the math, but as we multiply it out, the final product is 15%. This is called the product limit, and that is the final survival rate for this population. So, what does this slide say? That's not a very useful slide. I thought I was giving you some wisdom, but I'm not. If this helps you, fine. I don't think it does. But now I'm going to show you the easy method. I'm traumatized by that hard method. Let's look at the easy method. The easy method looks like this. These are our data. Okay, we have 6 patients. I'm not doing the pregnancy example. That's too long. Right? But we could, if you wanted to, we could. 6 people. At 4 months, patient 1 dies. At 10 months, patient 3 dies. At 14 months, patient 4 dies. At 24 months, patient 6 dies. Okay, so at 10 months, how many people are in my study? Well, at 10 months, 1, 2, 3, 4 are in my study because 1 has died and 1 has been censored. Okay, that's how to look at this graph here to give us a sense of what our data actually are. So this is the easy method. We create this chart. The first column of the chart is the time at which a death occurs. I say death, I mean event, because it could be a pregnancy or something else. So the time at which a first event occurs. So the first event occurs at 4 months. What happens? 1 of my 6 people dies. Okay. 4 months. 1 dies, right? I started out with 6, but 1 dies. So 1 out of 6 was the proportion who died, or 16% or so. Okay. How many are alive? Well, it's 16.7% minus 100, or 83%. Fantastic. That's my starting point. When does the next thing happen? Well, the next event happens at 10 months. Remember, a censoring is not an event. A death is an event, or a pregnancy is an event. The thing we're looking for is the event. The next event happens at 10 months. 1 person dies. Okay. At 10 months, 1 person dies. How many were alive? 4 were alive. 1, 2, 3, 4 were alive because that person died and patient 2 walked away. 1 out of 4 was the fraction who actually died, 25%. So the portion that survived that interval was 75%, or 1 minus that. Okay. What do I do with this? I multiply that by my previous survival fraction to give me a running total of 62.5% surviving from the very start of the study. 75% are surviving in this time interval, but 62.5% is the total survival rate at the point of 10 months. Okay, next event happens at 14 months. 1 person dies. Out of how many? 1, 2, 3. 3 are alive, 1 person dies. Okay, 3 are alive, 1 person dies. That means 33.3% died. That means 66.7% survived. Multiply that by my previous running total, and I get 41.7%. And I keep on going. Okay, so the last number before 0 is my final survival rate. So easy. So much easier than that ridiculous 2 columns and 2.1 nonsense, right? So you can choose whatever method you want. I recommend this one. So this is the Kaplan-Meier curve, is we simply plot these numbers. And we get that. Okay? That is the Kaplan-Meier plot for those data. Straightforward. An example. This is a real-life example. We have people in 2000 looking at aortic stenosis. That's the narrowing of the aorta. And they're looking at people who survived after something. I guess after stenosis was diagnosed. Okay. Now, before I look at the data, that final curve, that final percentage after we multiplied everything out, we call that the product limit. Or we call it the Kaplan-Meier estimate or estimator, or the product limit estimator, or whatever. I like to call it the product limit. Okay, that's what we call it. And the Kaplan-Meier product limit, you can do it at any given time, and that's the formula for it if you care. It's the number of subjects alive at the start of that interval minus those who died divided by those who are alive. Okay, same thing. The final product limit is one we care about, and that's the one That is the product of all of those individual KM estimates. So this is the data from that example I told you about. We find that the general population survival looks like this, but my clinical population survives like this. And I bring this up to show that you don't need to have in your clinical population your control group in it, because sometimes the general population is your control group. That shows us that everyone's dying, but the stenosis group is dying a bit more. However, the two groups are converging. I've got some homework for you. Here's some data you might want to try. I would like you to construct a Kaplan-Meier curve for these data and compute the final product estimate. And if that's too easy, well, separate out by sex. So consider these ones, the M's are men and the F's are women, and construct two different Kaplan-Meier curves and see if they are different for you. And if you can do that, then you've got it figured out. That's the hard part. Okay. Life expectancy is also calculated using life tables, and we can compute the total life expectancy by integrating the survival curve. And that's another mathematical step we can take. We call positive infinity omega, so we integrate the area under the curve all the way to omega to give us an estimate of that population's life expectancy. So this is the changes in life expectancy at birth in Canada over time. You see it's gone up over time, due largely to improvements in childcare. Okay? If I were to show you this going back 100 years, it's dramatic how much it's improved, due entirely to improvements in childcare. More recently, we're looking at improvements in elder care, right? As the extreme limits of upper life expectancy increase. If you look at it by gender, this is interesting, right? So women's life expectancy is going up, as are men's, but the men's are going up faster. We're converging now, and this might have to do with more female participation in the workforce, and so they're now engaging in the activities that used to threaten male health. It's equivalating a bit. Equilibrating, is that a word? I don't know. This looks at changes in life expectancy over time, computed at different times. So at birth, it's gotten better much faster than computed from different times. And this tells us that, again, improvements in public health interventions in extreme youth are paying dividends in the greater population. Most life expectancy curves look like this, or an S curve. Right? So people are alive. Most people are alive in their 40s and 50s, and so forth. So this shape is called a Gompertz function. Doesn't matter. It's just a little bit of a trivia you may care about. It's a funny word, Gompertz. Sounds like if you fart in the bathtub. Gompertz? No? Nobody? Fine. But I bring it up because you can look at interesting nuances in demographics from quickly looking at survival curves. Look at this. This is life expectancy at birth in America, separated out by sex and socioeconomic status. So if we look at men, those who are least deprived, the rich, versus those who are most deprived, the poor have a much poorer life expectancy than the rich. Not surprising. Over time, so the black is most recent and the gray is furthest away. Over time, everyone's life expectancy has improved, but that difference between poor and rich has maintained. It seems that the gap between over time has not changed as much for women, but look at this. For women, the gap between rich and poor has widened over time. Interesting, no? So we can ask further research questions by simply looking at that quick graph. I will stop there because I've confused myself and traumatized myself. I told you how much I hate this topic. Hopefully I've not expressed and shared my hatred with you, and you feel perfectly comfortable doing Kaplan-Meier computations, as you should. It's actually very, very simple, and the exam questions that I ask you are very, very simple, in my opinion. But if you can do the examples I've given you here, you will be fine. That is all, my friends, and I will see you in class, hopefully. Bye-bye.